Hey, I'm Nick Hodges with Gateway Ticketing Systems. Welcome to Code Rage 6. I'm here today to talk to you about unit testing with Delphi. Now, I've been out in front of a lot of Delphi crowds over the years, and many times I ask if people are doing unit testing. And I'm always surprised at the very small number of people who say they're doing it. So I'm here today to try and convince you that there's a lot of value in unit testing, that you can really reap a lot of productivity gains, and you can really improve the quality of your code by doing unit testing in Delphi. I'm going to start off here with some tweets by Bob Martin, author of the Clean Code book I highly recommend. And one day on Twitter, he was kind of going off. I mean, he was really fired up about unit testing. And these are some of the quotes he have here. My favorite one's the last one. If you have 100% test coverage, you can refactor savagely whenever you want with confidence. The other two there you can see talk about how you really need to test every line of code you're doing. So Uncle Bob knows how to write some clean code, and he really is behind unit testing. So I think that you guys all should be too. So here's my goal today. My goal is to make you feel like this guy right here. He is walking down the street naked. And my goal is to make it so that you get the feeling that if you are writing code without unit tests, you are like a guy walking down the street naked. You feel exposed. You feel embarrassed. You feel like there's something not right with what you're doing because you do not have unit tests for the code you're writing. That's what I'm shooting for today. So if I'm going to convince you to do unit testing, I'm going to have to give you a few arguments. So here they come. First of all, I want to be absolutely clear that unit testing is only a part of a larger suite of different kinds of tests. Now, chances are, because of the granular nature of unit testing is going to be the overwhelming number of tests that you write. But you also need to be doing regression testing, and of course unit tests immediately upon completion fall into regression testing. You need to be doing integration testing to make sure that the things that you've unit tested all come together and work together to form the project or product you're trying to build. And of course you need some type of acceptance testing, some type of testing system that says, yes, this is what we want to ship. Today we're just going to focus on unit testing. And that's the kind of testing that coders do. The thought behind unit testing, of course, is testing your code. The other kinds of testing, integration testing, acceptance testing in particular, are testing your product. But unit testing is focused on testing your code. Here's another important critical part of unit testing and what it is, so you can understand why you want to do it. Unit testing is atomic, and it leaves no residue. By atomic, I mean that you should be unit testing single entities that do one thing and one thing only, and that's usually, of course, a class. Now, of course, if you're following solid principles, you'll understand the single responsibility principle, meaning that your class should do just one thing. That means that your unit test should focus on testing just that one thing and no other. Leaves no residue part means that a unit test should not go off and invoke some type of external service or server or database or something like that and leave a mess behind that you have to clean up. If you're running your unit tests and at the end of it you think, oh, I have to write some code to clean up what that test did, then you are not truly unit testing. You're actually integration testing. You're testing the connection between your atomic thing and something else. If your code is leaving residue, then you're not truly doing unit testing. So this diagram here kind of shows the point I'm making, that your code is tested by unit testing. Your actual product is tested by other kinds of testing. So if you have clean refactored code and unit tests, your code can show proven functionality. You can really know that your code is supposed to be doing what it's doing and it doesn't do what it's not supposed to be doing. That's what unit tests can provide you. Properly designed code with unit tests is a powerful, powerful thing, because that peace of mind you get from knowing that your code works and the ability to change it as you refactor it while knowing that your tests are still passing can really add terrific productivity. So unit testing can also find existing bugs. Now there's a lot of talk about test-driven development, and I'll actually talk about that in a little bit. But you don't have to do test-driven development for unit testing to be beneficial. If you've got some code that isn't tested, there's no reason that you can't go back and write unit tests for it. And oftentimes those unit tests will reveal bugs. If you're searching and doing unit tests where you explore the corners of your code, as I will talk about here in a minute, if you're doing the things that you should with your unit tests, you will find bugs in your code as you write unit tests, even for existing code. And coming at it from the other way, unit tests can perform like bug repellent. They can help you prevent bugs from making it into your code base. If your unit tests are passing and you make some changes and your unit tests are failing, you have written a bug and the unit test will immediately reveal that bug, particularly if you're running those unit tests as part of a continuous integration system. Unit tests are really good at that because they don't change and they define how the class being tested should work. And if you break that definition, you'll know right away. Unit testing is like bug repellent. Unit testing also allows you to explore the edges of your code to make sure that it can work in all circumstances. For instance, you might want to check what happens with your code when it goes from negative to positive in terms of numbers, if you're adding or subtracting or something like that. We'll actually see that in our demo coming up. You might want to check to see what happens when the values might approach a certain limit inside of your code that you've placed, or if they try and go higher than the maximum integer value, or any other type of edge or corner case that you can think of. You can write unit tests for to ensure that your code works in the extraordinary circumstances, which will give you more confidence that your code works in the ordinary circumstances. Now, this is one of the features of unit testing that a lot of people don't believe, and is probably one of the top reasons why people don't do unit testing. Unit testing saves you time. It can save you a lot of time. First of all, unit tests don't add that much time to writing your code in the first place, because as you develop tests alongside of your code, you feel confident that you know that your code is doing the right thing, and you don't spend time ensuring that it is. If you write a test, implement, and then the test passes, now you know your code works and does what it's supposed to do, and you don't have to worry about it and spend extra time sort of wondering whether it does, or even for that matter, writing more code to make sure that you defend against things that might never happen. Secondly, because unit testing allows you to make changes to the code, they can save you a lot of time in maintenance and in refactoring by proving that the code still works properly. You can make changes quickly and easily with confidence because you have unit testing backing up all those changes. All of that stuff adds up to saved time. And finally, this may be the most important thing to many of you, is that unit testing gives you peace of mind. Once you have a complete suite of unit tests running against your code on a continuous basis, day in, day out, and they're all passing, you can feel really good about your code. You can know that it's doing what it's supposed to be doing. You can know that that code is not broken. And you can know that what it's doing is what it's supposed to be doing. And it's not doing stuff that it's not supposed to be doing. You'll know right away when a bug occurs in that code. And all of this adds up to peace of mind. Peace of mind is good because we know that what we write is doing the right thing. Okay, so now I want to talk a little bit about a point I made earlier, and that is that all unit testing should be done on atomic entities and should have no residue. Now, normally when you write unit tests, you have this test driver, some kind of test harness that pushes a class, pokes it, asks it to do something. The class does that. It returns a value, and you check that value in the test driver to see if it's exactly what you're expecting. Now, when you do that, you actually have to fire up an instance of the class in order to get it to do things. And sometimes when you create a class, there can be all kinds of side effects. And this is really important when designing your tests because you want to make sure that your class doesn't have side effects. As I said, you don't want there to be any residue. For instance, you might fire up this class and it could fire off 2 more classes in its constructor. That might talk to an external database. You might have another class that chains off to something on the file system or some hugely CPU intensive process, or another class might even go off and talk to another server and start charging your credit card against something. I don't know. Anything can happen. What you want to do is you want to make sure you understand each class's seam. That is the point at which, or the position of which, the class itself begins communicating with the outside world. And that is the point at which you want to control for the purpose of doing unit testing. When you do unit testing and you've figured out where that seam is, what you can do then, of course, is you can provide a different solution outside that seam. Maybe you talk to some friendly class that's outside the seam, like, say, a t-string list. It's no big deal if you fire off a t-string list, right? That's not really going to do much. You might have a stub class that behaves exactly like this class, with the exception of it doesn't do anything. The classic case here is a logging class. And your stub logging class simply accepts the logging call and doesn't write it to any log anywhere. It just says, oh, yeah, thanks. And then, of course, the third one, and we'll talk about it late in the talk here, is a mock class. That is a class that pretends to be something else. Typically, this would be something like mocking a database connectivity class that will give back answers that make sense for the questions that you ask it, but doesn't actually ever talk to a database. Or it might mock up or pretend to be an external web service that you don't want to call every time your unit tests are run. So it's very important to understand this and to see that every class needs to have a seam so that you can control what happens when that class is tested. So I'll just give a quick word here about test-driven development. I haven't really talked about test-driven development. I'm not really dogmatic about it, and I highly recommend Kent Beck's book on the subject. But the basics of test-driven development really are, you write the test that you expect to pass before you write any code. Then you run it and it fails. And then you write some code until that test passes. Then you do that at the smallest, most incremental level that you can possibly think of. And you continually do that. And you build up a cadre of tests that pass. And you eventually are able to implement your entire functionality. And then you end up with functionality that works. The bottom line that I want to make sure everybody understands too is that if it's hard to test, if it's hard to write tests for your code, then you're doing it wrong. You need to be able to write code that knows where that seam is, that is easy to provide mock, stub, or simple classes outside of that seam in order to create unit tests that are really, really easy. If you're having a hard time writing unit tests, or if the reason you don't write unit tests is because you say, oh, it's too hard, that means that you're doing it wrong. Now I'm going to talk a little bit about exceptions as well. When you write frameworks, chances are you're going to raise exceptions, and your code does exceptional things. You raise exceptions. And one of the things you do when you write unit tests, of course, is you want to poke your class so that that exception gets raised, and then make sure the correct exception is raised in the correct circumstances, and that it's not raised in circumstances that it shouldn't be raised in. So we'll take a look at that here in the upcoming examples. And finally, we'll take a look at using mock objects and how some of the new features in Delphi XE2 enable a mock object library. Boys at Vsoft Technology, the guys that write the great tool Final Builder, have actually put together an open source Delphi mocking library, and we'll take a look at that to see how you can actually write mocking classes that are really easy to define for your tests to simulate classes and functionality outside that seam, as we talked about earlier. Now when you do unit testing in Delphi, currently you're almost certainly going to be using a framework called DUnit. And DUnit is, of course, a unit testing framework for Delphi. It ships with Delphi, as I said, and it generally adheres to the XUnit principles. And if you want to find out what those are, you can look XUnit up in Google. And it takes advantage of the old RTTI by allowing you to publish or use your tests in the published section. It sees those tests and it automatically runs them as part of the framework. You can use DUnit to run your tests at design time, so you have your nice green GUI bar going along, or you can set it up as a console application that runs as part of a continuous integration system. And in case you're wondering about the picture on the right there, that's the only picture I could find that made any kind of sense at all when I typed DUnit into Google Images. It just happens to be a PlayStation game called DUnit. Okay, so enough slides. Let's start looking at some code and what you can do in Delphi with unit testing. Now the IDE does provide you with some nice support for setting up a unit testing project for a class or an interface that you've already defined. So here I just have a real simple package with a real simple unit in it, and I've got a class declared here. I've actually written no code yet, so this is fine. I have the stubs here, I basically have this class. And what I can do then is tell the IDE to create for me a new test project So I can declare a test project, and that will add the given test, bring up this wizard, ask me some few questions. My source project is the demo package there, and I want to create a project called demo package tests. I'm going to put it there, and obviously it's for the personality, and I want to add that to the project group. By default, I want to have it be the GUI test runner. I mentioned earlier you can have a console test runner, but we'll use the GUI test runner because all good unit testers love to see that green bar go across on the GUI runner. So we'll finish that, and it'll create us a new package, a demo package test project. And then we'll go in, and on top of that, we will add a test case. Now what's going to happen here is the IDE will go and look at the project for which the demo package tests is written. It'll look for classes, and it'll find the methods in those classes, and ask you, do you want to create test stubs for these classes here, this class and these methods, excuse me. And you say yes, and so you click next, and asks you what the file name is. You can accept the default, so you can change them as you want. And then you click finish, and now the IDE has created a basic testing framework for your class. It has set up tests for all three of the methods in that class. It has created a default instance in the setup procedure here, and the teardown procedure frees up that class. And so now basically you've got everything you need to be set up to write unit tests for the class that you had. Okay, so now we've seen what support the IDE can give you when you're writing unit tests. It can create a nice framework that you can then add on to and build up. If you make additions to your class, add methods to it, for instance, you can rerun that wizard, and it will pick out and find the methods that you added and add those to the test harness, the existing test harness. So that's a nice thing. But now let's take a look at a project that will allow us to look at some of the basic ideas behind how to write unit tests and why you want to write unit tests, as we talked about earlier. So here I have a simple calculator project, and inside of it is this unit called tCalculator that is sort of the beginnings of a calculator class that might be used as the class behind a GUI where buttons are written. But of course you don't ever want to really write the GUI. That's secondary. What you really want to write is a good class that can stand alone and do the calculator things. So right now it basically only implements addition. We'll be implementing subtraction here in a minute to illustrate sort of some test-driven development principles. It's a pretty simple, straightforward class. It's got a clear button, the method that represents the clear button, methods to represent entering a number, pressing the plus button, pressing the equals, calculate what's going on, and then a property that actually holds the number to be displayed. It's all integer based. There's no floating points. Very simple class, but just illustrative here for our purposes. The real interesting part, of course, takes place over in the unit test case, which descends from test case. We have our own test calculator here. I've written a little helper class here called add numbers that basically goes through the process of clearing, entering, adding the plus button, entering another number, and pressing equals. That's a pretty standard thing to do when you add, and then returns the result of whatever the display value would be. So that's our little helper value. And here you'll notice that I've got a nice published property called test addition. The test addition method comes up with a bunch of tests, and a test inside a DUnit is basically the declaration of an expected result, a test result, which in fact calls the class and gets the class to do the work, and then a series of calls that actually check the actual values against the expected values. And that's what this check equals call does. And the check equals call is strongly overloaded. If you look at it in the IDE, you'll see that there's any number of items that you can check as being equal inside of the framework. There's also a number of other check values as well, such as there's a check boolean, check boolean, check true, check false. Generally, you want to avoid the check booleans because if something fails, all you get is expected true but got false. You should prefer to use check equals instead, so where the error message will tell you expected 5 but got 4, that kind of thing. But there's a number of overall things here. You can also do check not equals to do negative testing, i.e. Pass in a result and make sure it doesn't return something that you want. So there's a number of powerful check values in the framework itself. So in the end, all you're doing really is checking the value of that the framework or the class under test gives you, writing in the expected result, and calling check equals. If the two are equals, the test will pass. If the two things that you pass in to check equals are not equals, or whatever it is that whichever check method you're using proves to be false, then the test will fail. So let's take a quick look just at how this works. We'll run the application, and you'll notice now we've got our DUnit GUI here, and I've checked off all these tests, and I'll run the test, and you'll notice I got my nice little green bar that came across here, meaning all my tests passed. So right now I feel confident that if I add -1 and 3, I get 2. If I add -10 and 3, I get -7. If I add -10 and -3 together, I get 13. You get the idea. And you can write as many of those tests as you want. And you'll notice that I tried to add 2 positive numbers, 2 negative numbers, one that returned a positive result and one that returned a negative result. 2 negative numbers that definitely obviously are going to return a negative result as well. So I tried to check the borders. I tried to go across zeroed, those kinds of things with our tests. And these are very basic, straightforward tests that allow you to check to see if your addition method worked. Let's go back real quick and just see that, yeah, my addition method probably does work. It's pretty simple, pretty straightforward. When I call addition, I actually just, add 2 numbers together. That probably works. But for illustrative purposes, I think you can see how these unit tests would work. Now, curiously, there is a way to avoid sort of having to make these numbers up and put them in here all at once. If you want to add another test, you want to check to see what happens if you add really big numbers together, or if you try and add a number past max int or something like that. You're tempted here just to take this thing and copy it, paste it in there, and fix it up, that kind of thing. Put some big numbers in there and run your test. But that gets a little cumbersome, and copy and pasting can be problematic, of course. You want to generally avoid that kind of thing. So I just want to show a quick way here to sort of allow you to add data and draw in data to your tests. And so first of all, to do that, I create this new type called a calculator record. Basically, it's 2 integers and a result, and it's got a constructor on it that allows you to pass in two values and a result. And of course, this could be for anything. When we do subtraction, we can use this. You can use multiplication, whatever. It's pretty generic. It doesn't imply any particular operation. So then here's the implementation of the constructor for that class. And the next thing I do is I declare a tCalculations method, record here, or type here. It's an array of the tCalculation record, so it's a whole array of this particular record. And then I write a function here that will declare and create, a bunch of these records. And you'll notice that I have the calculations record that's created, and into it I pass a whole collection of tCalculator records that I actually create. There's actually a whole bunch of them here. I can maybe format this a little better. But here, as you can see now, if I want to add a test, I simply add in another tCalculator record. And now you see I've done things like, maxint plus 1 checks out to be maxint plus 1. All those different things. I can start setting up values inside of my tCalculate record in order to make it real easy. Now if I want to add another test, I can just, for instance, copy this, add it in, and now I can prove that 1 plus 1 is 2. Now the way you then run your tests here is you can actually simply create an instance of tCalculations, or get that using the create calculations method here, and then I can just iterate from low to high values of that array, pull out the expected result, which is of course the third member, add together A and B, the first two, and then check to see if those are equals. And this enables me to very easily add a test without actually having to sort of do this clumsy cut and paste value up here. It's a much cleaner way to add tests, and particularly for things that are calculating or somewhat algorithmic, where you have known inputs and clear outputs like this. That is a nice, neat way to test a whole lot of possibilities. So now you can see, uncomment this method up here. Now I'll run it, and you can see that all of our tests still pass. And when I say everything's green in the unit testing world, that means that the GUI runner you use has given you nothing but green. If a test fails, you'll get purple. If a test raises an access violation or some other exception, you'll get red. Those are all things you don't want. You want all your tests passing. You want green, and it's all good. Okay, so let's carry on with this scenario. Let's go back to our calculator class, and we'll go ahead and we'll implement the press subtract button. First, let's do it kind of in a somewhat test-driven way. We'll comment out the functionality first, like so, and then so in other words, we said, okay, we're going to create a method, but we're not going to implement it yet. We're going to go over to the testing harness here, and we'll go ahead and I'm going to comment out this declaration of the class, and I'll uncomment out this declaration of the class that now has a whole bunch of subtraction functionality. Here's the helper method for subtract numbers. Let me go down and uncomment them down. All of this down here as well. Here's the subtract numbers methodology. I clear. I press enter in one number. Press the subtract button, or simulate that anyway in this class. Enter another number, press equals, and see if the result is what I expect it to be. Here's a bunch of subtraction calculations. 2 and 2 minus 2 is 0. Here I'm texting some negative numbers, some positive numbers that result in negative numbers, some bigger numbers, any set of possibilities here I can test. Let me reformat it just so that they all line up. And again, this is using that data-driven, sort of code-based data-driven solution. And this is exactly what you'd expect here. As before, I clear the calculator out, I say what my expected result is, I say what the test result is, and I call check equals on the first two. And here I'm actually using the optional third parameter, which is creating a custom message, which isn't very nice, I suppose, but it's just kind of showing that you can control what message is given out when the test fails. Now, if I run this test, let me save it all. If I run this test, it'll fail because we haven't implemented anything yet. And here's the purple, kind of the, well, it's kind of a, what is it? I don't know what the color is. But it says, hey, you can't subtract. It failed for 1 and 2. And once the test fails, inside the method, the entire test stops, and it only attempts to run the very first set of data. And once it fails, it stops. So now let's go back and let's implement the subtraction method. So we go and say, okay, now our test fails. We're going to implement the subtraction method, and we'll think, okay, good, it's all good to go. We keep track of the operation, we keep track of the state, and let's run it again. And uh-oh, it still fails. And we think, why? That implementation is exactly the same as the addition implementation that we have above here. That should work. I'm not going to go through the debugging scenario, but this is a good example of, okay, so you implement it, and it doesn't quite work like you think it does. So, and it turns out when you actually start subtracting, you don't want to calculate when you press the subtract button. That will set the display twice rather than once, and it actually kind of indicates that there's a bug in the way we're doing the addition as well. But point being that you think you implemented it and it failed, and you know it failed because you wrote the test. You didn't go happily on thinking that this was going to work and then only discover later on when you actually deployed the thing or something. You knew right away that this method didn't work. So let's comment out this bad one, and actually here's an implementation that's correct for our given scenario. And now I can save that, run the test, and they all pass and it's all green. Just wanted to show that writing the test first can actually help you know that your initial implementation might not be right, and that you can easily and quickly, right off the bat, within minutes, within seconds, write up the correct implementation based on your failing test. Okay, so next up, let's take a look at that exceptions and how to test exceptions, as I mentioned. Here, I've got a little class that's just called the exception raiser. I can either raise an exception or not raise an exception if I want to, depending upon whether I call which method I call. The raise exception method here, of course, just simply raises my declared exception here called testing exception, and the not raise exception just creates some silly string and returns that. So now I have the option of either raising an exception or not raising an exception. Neat little class, huh? But I got in also over here I have a test class that will test this exception raising functionality. So I actually have 3 ways of dealing with exceptions in DUnit. 2 are supported by the framework, and 1 is actually, I think, the coolest way, using anonymous methods, that lets you use an anonymous method, obviously, to check the value of an exception. So the first one is, we'll test that the exception is happening using the exception wrapper. And here there are two methods that you call inside of DUnit called start expecting an exception, and you tell it the class type that you're expecting. You run your code, and then you stop expecting that exception to be raised. And once you stop expecting that exception to raise, the framework will actually check to see that the exception was raised, and if it wasn't, then it'll tell you. So that's the first way. The second way is you can call a function called checkException. You can pass in an exception raising method reference as the first method, and then the the first parameter, and the second parameter is actually the type of exception that should get raised. Now, this is a little clumsy because you have to actually declare this exception raising method here and raise the exception inside that, and but it's a little less clumsy than this one, I think. But the third way is actually really cool, and this is actually test with anonymous methods, and this uses a function called checkForException that I have actually added to the class, by the way, courtesy of Alex Ciabanu, one of the guys who was a former Embarcadero guy who worked on the RTL and worked on the DEHL collection classes and done a lot of cool open source stuff with Delphi. So basically, this one tries to run the code that you pass in as an anonymous method, and if that code raises the exception that you're expecting, then it sets the exception to be true, and if it doesn't, then it just goes ahead and assumes the default false, and it just calls this check boolean value, and if the was exception value is false, it gives you the message that you can pass in saying, hey, sorry, you didn't raise the right exception. I just thought that was kind of cool. So now if we run this, you'll see that our exceptions all are called correctly. Now, just to prove, in case you were wondering, I ran that outside of the debugger. Now if I run it inside the debugger, of course, the exceptions get raised. Here's this exception is supposed to happen. That's the message from my exception. I can hit continue, and there's another one. It's supposed to happen. Again, it's supposed to happen. You saw the exceptions get raised inside the IDE, and now I still have green. So that's a way you can actually check to see that your code is properly raising the exceptions that it's supposed to. Here's the call to check for exception. I expect an e-testing exception, and here's the anonymous method that gets called and the error message that should never actually be called. Just for fun, let's comment this one out, uncomment this call here, which actually calls the no exception raised class, and you can see that implementation, when run, will actually fail because the exception was not raised. Okay, and finally, we'll cover the concept of mock objects. Now, oftentimes, your classes, as mentioned earlier, might go off and call another object out somewhere in the world or in your system or anywhere, really, that is an expensive operation for whatever reason. It might be expensive in CPU time, it might be expensive in that it's writing to disk, it might be calling a database, it might be doing all kinds of things that you don't want it to do while you're unit testing. So that is where mock objects come into play. Mock objects can replace those expensive objects that the object under test uses with an instance of an object that behaves in the same way as that expensive or costly or time-taking function will, but instead it pretends to be that functionality, allowing you to test your class in isolation. So here's a simple instance of an adding machine, and again we're going to use the old adding. It's very basic functionality, but it has the concept of an external device that's going to add two numbers together for you. So you create an instance of it, you pass in the adder that you want to use, and you add two numbers together. That's the only function it does, and of course what it does is it calls your adder and it returns the result. Now you might have an adder that just uses addition. You might have an adder that calls a soap service somewhere or whatever. In our case, we've created an adder interface and then we've declared an implementation of it, and in this case we're just going to add the two numbers together, right? But what we'll do is we'll just pretend that this is a call out to some supercomputer at Stanford that costs $249 every single time you call it, right? And to represent that, we'll just show a message called ka-ching every time we call this service, right? And that's not good. if you're going to run unit tests every time you check in as part of your continuous integration service, that is not something you want to have happen. You don't want to be charged $249 every time you use your interface. Here we go. We're going to run some tests on this thing. And what we've done here is we're going to use the Delphi mocks framework, which can be found here, written again by the folks at Vsoft Technologies, released as open source to the community. Very, very nice set of code, and it takes advantage of some really cool features in XC, most particularly the T virtual interface class, which is a class that can implement any interface at runtime. So what you can do then is with these Delphi mocks is you can create a mock for a given interface and implement it however you want. And in this case, you can, with Delphi mocks, you can tell the mock class what to do when a specific method is called, and we'll show that here. So first of all, the first instance here, or the first test we've got, basically creates this adder. It's really expensive. It calls the adding, creates the adder that we had before that's going to call out to our $249 per call adding machine, and it's going to pass that into the adding machine. And then we're going to create an instance, and I need to comment this out here. We're going to go ahead and pass in A and B, the values of 2 and 3, and expect to get 5 back. So once we do that, we can run this, and you will find that that will indeed work. But uh-oh, ka-ching, we got charged $249. Uh-oh, ka-ching, we got charged $249. In other words, every time we run this unit test, we are going to incur a cost of some expensive external service. We don't want to do that. We want to make sure our adding machine works, but we want to do it in such a way that we don't have to call out to that function out there. So to do that, let's not create an instance of our expensive one, but instead let's create a mock object that knows how to properly respond to the calls of the iAdder interface. So in this case, we're going to create a mock object passing in this as a generic type iAdder interface. And then the mock object can be set up to return specific values when specific methods are called. So in this case, the setup process will return the value of 5 when the add method is called with 2 and 3. And the cool thing I want you to note here is that this class knows that it is going to use an iAdder interface, and so for instance right here you get full support for code completion using the IDE. Now the other thing too, I'll just comment out this thing called expects, and we'll worry about that in a minute. So now you can see when we run this, we will get a passing test but no ka-ching. So in other words, we are now able to test our adding machine functionality without ever calling any external adder. We've created sort of this fake adder, this mock adder that knows how to return certain values when certain tests are called. Now you can also say you want to expect that 3 and 2 actually does get called. You want to verify that that particular thing does get called, because sometimes more complex tests will be a little harder to ensure that everything does get called. So you can say, hey, for this mock object, I expect that at least once we will get a call to add 3 and 2. And then at the end we can verify that that indeed happens. And all is well. Now you'll notice that, for instance, if we said, well, we're going to try and we expect to at least once get a call to 34 and 2, well, that will result in a failure with the message, of course, 34 and 2 is never called. So the mock object can even report back to make sure that all the scenarios that you set up as mocks were actually called. But the real cool part here is this notion that you don't ever even have to call an external service, right? This mock object knows how to pretend to be an iAdder interface. You can tell it what it will return, what is expected to be called during the process of all the testing. So You can connect up all your method calls and ensure they're called. And you don't ever have to use any kind of external service. And that is a feature in XE2 that is really, really cool. So that's a quick look at mock objects. Okay, so there's my pitch to get you to do unit testing. We've seen how you can do it fairly straightforwardly. We've seen that it's pretty easy to do, and we've seen some instances of how you can make sure that you test your classes in isolation using mock objects, how you can use tests to ensure that you discover bad implementations right away rather than wasting time with bad implementations. So I have some final advice here. My final advice is this. First of all, I think that you should only test the code that you want to actually work properly. You know, everybody says they don't want to write tests because it takes too much time. So yeah, fine. Only write tests for the code that you want to work properly. If you've got code that you don't want to work properly, don't test it. Go ahead, don't write tests. But only test the code that you want to work properly. And at the same time, don't test any code that you want to be buggy and to cause you problems down the road. If you've got some code, I don't care if it's buggy, I don't care if it causes me problems down the road, go ahead. Do not write tests for that code. Because, I mean, if you don't care if it's buggy, you don't care if it's causing you problems down the road, you don't care that it's going to be hard to maintain, hard to find bugs in, hard to fix, all that stuff, fine, go ahead. Don't test it. Okay, that's my talk, that's my pitch. Hopefully I can convince you to write some more unit tests. I appreciate your attention. And I gather that now I'm here to answer your questions.